Hi, Dr. Wang here. Now we're going to make a concept map for the trip operon. Trip operon contains a couple of genes that encodes enzyme required for the synthesis of tryptophan. Tryptophan is an essential amino acid. Before making this concept map, it's a good idea to watch the video first. You can go to Commons page, book Molecular Biology, Gene Regulation, and then it's the same video where the lac operon is, but the second half of the video. Coming back to this assignment, so here are all the terms that we will connect in the CMap. I have these terms already in my map over here. So the first thing we're going to do is to connect the DNA elements that basically make up trip operon. So those are in gray, starting with the promoter region, followed by the trip operator, and then followed by the coding genes. The promoter, trip operator, and the 5 coding genes are located next to each other on the chromosome. So this forms the trip operon. The 5 coding genes encodes 5 enzymes in the tryptophan biosynthetic pathway. The function of those enzymes is to produce tryptophan, which is an essential amino acid. The trip operon is suppressed by the trip repressor. This is a protein that's capable of binding the trip operator and deactivate the RNA polymerase block. While the trip repressor binds the trip operator, it will prevent RNA polymerase from transcribing the rest of the coding genes. The trip repressor is encoded by a gene called TRPR that's located elsewhere. When tryptophan is present, it's going to bind and activate the trip repressor. When tryptophan is present, it will bind and activate the trip repressor. When trip repressor is functional, it binds the operator and blocks RNA polymerase from transcribing the operon. So RNA polymerase is off, which means the entire operon is off. When we look at the logic here, the presence of tryptophan is going to eventually lead to the shutdown of the entire operon, which means no new tryptophan will be produced. This makes sense because the E. coli won't really want to waste energy producing enzymes when there are plenty of tryptophan available. On the other side, if tryptophan is not available, this means E. coli will have to produce its own. So when tryptophan is not present, it won't be able to activate the trip repressor. So trip repressor is not activated, which means it cannot bind the operator, it cannot block the RNA polymerase. So RNA polymerase will be turned on, and then that's going to lead to the transcription of the coding genes here. So as you can see, the logic here is when tryptophan is not available, the operon will be turned on, and then that will allow the E. coli to produce tryptophan for itself. Now we're going to put the trip operon and the lac operon side by side. And you can see that there are features that are very similar to each other. So the operon is made of promoter, operator, followed by a number of coding genes. And the operator is bound by repressor, and the binding of the repressor to the operator prevents RNA polymerase from transcribing the coding genes. So, however, the logic is slightly different. So here, this molecule, tryptophan, activate the repressor, while over here the lactose inactivate the repressor. So here we can see that this is a negative feedback loop. Less tryptophan is going to lead to production of more tryptophan. While this is a positive feedback loop. So lactose is going to lead to the production of enzyme that's capable of using lactose. And there's a reason for this. The trip operon belongs to the anabolic pathway. So this is a pathway that builds up the biomolecules or making things. So the logic here is to produce the compound only when it's necessary. So if tryptophan is already available in the media, then there is no reason to produce it. On the other hand, the lac operon belongs to the catabolic pathway, or the pathway to break down biomolecules and to generate energy. So when the molecule is present in the media, then it's necessary to turn on the operon. So E. coli can utilize lactose to support its growth.